I think scientists like to think of themselves as creative, and certainly I have to show the obligatory Einstein slide here. Let's consider, say, Isaac Newton and then Einstein. Isaac Newton was revolutionary in his time. He looked at gravity, at light. He looked at laws of motion. He gave us the laws of motion that explain how speed and things determine the way matter moves around. And he considered speed to be something that we can vary. And he considered time, on the other hand, to be something flowing steadily at the same pace all the time. What Einstein came along and did was he considered, what if we take the speed of light in a vacuum as being a constant, unchanging? And that leads to this strange idea that time is a variable. It doesn't make sense to those of us who live by the clock. But when he explored this idea, he asked this question: what if he came up with some revolutionary answers, some very creative answers, that helped explain a lot of things that we didn't really understand? And so he asked the big questions, and I think that's very important in science. So I'd like to consider, in 2019, what are the questions we need to be asking? What are the big questions? Well, to do that, we need to consider, where are we currently? And currently, we do know quite a lot. In my field, chemistry, we have the periodic table fairly well worked out. We know how the elements relate to one another. In physics, we have all sorts of exotic forms of particles and matter, the Higgs boson here. And the biologists and others have figured out many different forms of life, exotic forms of life. And I would say we're even beginning to understand how the brain works, which is pretty amazing. In my particular field of organic chemistry, and I'm really a synthetic organic chemist, making things, we can make some pretty amazing things. This molecule here was made 30 years ago, and it's incredibly complex, but we have very powerful ways to make things. So have we worked everything out already? Is everything already done? Well, I would say we're kind of stuck with a certain type of thinking that constrains us just to the familiar. The very language we use about chemistry or physics or anything is constrained by the fact that we live on this planet with this temperature, this gravity, this atmosphere that we're working in. So I'd like to ask you, does this look hot or cold to you? All right, it's a picture of the Arctic, and most people on planet Earth would consider this to look cold. Of course, if you're in Potsdam, New York, this may look like a warm January day, but the point is, whether you consider it hot or cold depends on where you live. And so the language is framing our perception of things. And that's limiting our creativity, I think. Let me give a chemistry example here. A substance that's a pretty fundamental concept in chemistry. And this is a pretty good definition. So a form of matter that has constant chemical composition and characteristic properties. That's a pretty good definition, and it is a fairly absolute definition. It's not fixed by being on Earth, or is it? Let's look at this substance here, ethylene glycol, which you put in your car radiator to stop it freezing. This is the structure as we draw it on planet Earth. And this is one substance, is how we define it. But if we go somewhere very cold, like Pluto, certainly once we get very cold, this resolves itself into 3 different structures. And these are all, in a very cold place, these are all different substances. But we don't call them that on Earth, we call them conformations. So what my students learn to call them, because on planet Earth, these are all the same one substance. If we go even colder, we start seeing more and more structures freezing out and becoming separate things. Now these aren't just different ways of looking at things, these are actually compounds that have different properties. So in other words, what we're doing is we're always looking at our science through an Earth lens at everything we do. Now there are a lot of different variables that we can change. Temperature is just one of them. We can change the gravity. We can change the atmospheric pressure or even the atmosphere. We can look at things like magnetic flux or other forms of radiation. And once we start to consider these, our minds start to explode because the possibilities are mind-boggling. We can't conceive of what it would be like to be at these immense pressures and temperatures and different gravities. We simply can't conceive it. So what we're doing, though, if we constrain ourselves to that, is we're missing so much. So rather than it simply being a frightening thing to consider, I would like to consider it an opportunity for us to get creative, especially when we look at the sorry state of science today. So this is how much we know, is that little red smudge near the bottom left of the screen there. That's everything we know about science. If we consider this to be like 3-dimensional creativity space, then we're missing out on so much. We need to start exploring different pressures, gravities, etc. And once we start to do this, I think there are amazing possibilities. We're going to find new forms of matter, new ways to make matter interact with energy. Maybe even we'll understand space-time, and it's not just Doctor Who, it's going to be something amazing. I like Doctor Who. Scientists have long looked into the universe, and in fact many great discoveries have been made there. It is a very fruitful form of research, and helium wasn't discovered in birthday balloons, it was discovered in the spectrum of the sun. And a new form of carbon was found about 30 plus years ago, looking at the spectra, the infrared spectra of distant stars. And it was, both of these things are now commercially available substances we can get on Earth. So this is certainly fruitful, but I went into chemistry because I was fascinated by the idea of change and the ability to make things. We can actually change the inherent properties of the materials that we have in front of us. And this is just one example, I think, from the 2016 Nobel Prize. Molecular machines, making molecular gear wheels. What amazing things chemists can make if they start not just to observe the universe, but actually to get creative with what we find. And that's what I wanted to do in chemistry, and what I did as both an industrial chemist and an academic chemist. But I feel like we've been constrained for too long. We're stuck with this earth-based thinking, and it's like an artist who is only going to ever consider working black and white. There's nothing wrong with black and white. There's nothing wrong with Earth-based chemistry. But we need to consider, I think, the whole color palette. We want to use all the colors, not just be constrained to this one black or white option. So in the same way, we need to consider all the possibilities of temperature and pressure and so on. Now, this isn't just some abstract idea. This is something that's going to happen in our lifetimes. And this may seem very science fiction-y, but these are plans currently going on. Obviously, these are artistic renditions of them. But the Chinese plan to put a base on the moon. NASA plans to put a base on Mars. So we're going to have to learn to adapt to work in different environments anyway. And these are challenges facing us right now. And our chemistry right now doesn't have the answers. Let me explain that little acronym, ISRU. And that's, I think, a rather crazy acronym, In Situ Resource Utilization. It's just a very fancy way of saying we want to be able to make the things we need from what we find locally. We kind of do that when we try and buy local produce. In a sense, we want to use the local resources. If you're on the moon, you want to be able to use moon stuff to build your base from. You don't want to have to haul everything up from Earth. That's pretty expensive. If we're building a Mars base, we want to make things from local Mars materials. Now, that will require us to find ways to do chemistry that's suited for Mars. There was a serious proposal for a Mars factory a few years ago that suggested we should launch a nuclear reactor from Earth, send it up all the way to Mars, and use that to power a huge factory based on Earth-based processes. Earth-based processes rely on cheap heat. We can burn coal or oil and get very high temperatures very cheaply. That doesn't work very well on Mars. All we can do with local materials is to use the rather feeble sunlight. The temperatures are colder, so we have to adapt our chemical processes to work at temperatures lower than on Earth. And we don't have plentiful supplies of water. There is some. And we don't have plentiful supplies of coal to burn, and so on. We have to adapt it for the environment. Now, green chemistry is, to me, one of the most revolutionary ideas of recent chemistry. And that's the idea, I would describe it as being, let's make our chemistry, adapt it to the Earth environment. And if we do that, we find that our chemistry becomes more efficient and more effective. If we don't produce a lot of waste, our processes are actually more efficient and actually cheaper to run. We're not wasting as much. We can apply the same principle to exochemistry here. We already do this, or have done for millennia. People living in the Arctic have long used materials from their local environment, and they eat food found locally. Meanwhile, people, this is Sumba near the equator in Indonesia, they use food that's local, and they use materials that are local for their houses. You wouldn't live in the Arctic and ship all your food from the equator. You want to find local materials. We want to be doing the same thing. So we don't want to build a Mars factory that looks like this, that's an Earth-based process, and drop it on the surface of Mars and say, we'll run our processes at 1,000 degrees centigrade. We want to find ways to adapt it to the environment. The best way to do that, think like a Martian. If you were someone who'd grown up on Mars, you would naturally do chemistry that's fully adapted to the Mars environment. If you grew up on Pluto, you would have completely different solvents and ways of thinking. We need to be doing the same thing. It's hard for us to do that, but our ancestors adapted to many different environments on Earth. Why not do the same when we think about our chemistry? It will expand our creativity. Right now, as I see it, we as scientists are in this very comfortable, warm valley. It's lush, provides everything we need. It's what we're familiar with. This is our comfort zone, if you like, of creativity. But if we want to really explore the limits of science, we have to get outside of the constraints of that little valley, which represents Earth, and look at some extremes. Things which are hostile and alien to us if we've never left the valley, but which will push our creativity. The mountains, the oceans. What amazing things there are. The people in the valley don't even know about them. They've never left the valley. What about the deserts? What about lava lakes? These are extreme environments on Earth, and all we're doing is staying in this friendly valley where we feel comfortable and warm. I think we as scientists need to look outside of our comfort zone and explore the extreme environments that await us in space. And when we do this, we'll find amazing beauty and amazing new discoveries. They're just waiting to be found. Thank you.